Hello, everyone. Welcome to the webinar, Cool Innovations, Next Generation Thermal Management Materials for Emerging Technologies. My name is Ren Yu, Senior Director here at Lux, and I will be moderating today's session. Presenting today is my colleague, Akshay Chaudhary, analyst here at Lux, leading our coverage in thermal management materials. Now, throughout the webinar, you can type any questions that you have in the questions box on your screen. Time permitting, we will answer all the questions that we can. Now, if your question does not get answered, please do not hesitate to email it to questions@luxresearchinc.com, and someone will get back to you shortly. Now, if at any point you experience technical difficulties, such as a frozen screen, simply refresh your browser and check that your internet connection is strong. Now let's jump into the presentation. Over to you, Akshay.
Hello, everyone, and thank you for being here. I'm excited to dive deep into some cool innovations in thermal management materials for hot emerging technologies. And I promise this is the only pun we have in this presentation. So today we have a packed agenda. We'll first start by exploring the unmet needs across various industries. Then we will dive into the exciting innovations happening throughout the thermal management materials value chains. And then finally, we will discuss outlook and highlight potential disruptors. So let's start by exploring the key unmet needs across industries. Over the past few months, we had numerous conversations with our clients, and three key themes emerge in these conversations: electrification, digitalization, and sustainability. And these are the driving forces shaping innovation and industry today. So last year in South Korea, EV fires spread rapidly, destroying 143 cars, causing significant property damage. And the incident forced the government to introduce new safety regulations to ensure battery safety. So safety is a top priority, especially in electrification and EVs. So reliable thermal management is very critical here. AI data centers, on the other hand, like the ones behind ChatGPT, currently use 460 terawatt hour of electricity. And if the growth continues, this could rise to 800 terawatt hour by year 2026, and with nearly half of this used for cooling. So the focus on enhancing cooling efficiency while minimizing the energy consumption is a key priority here. Sustainability is a key theme across industry. And in refrigeration and cooling, a major challenge is the global warming potential of these heat transfer fluids. And also, there are some concerns around PFAS content, leading to regulatory pushbacks as well as bans. So it is crucial for industry to ensure the materials used in various thermal management systems have a minimum environmental impact. And as a result, companies are increasingly driving the innovation across the value chain. And this is particularly evident in thermal interface materials as well as in insulators, which is also directly reflected in this patent filing activity. So to track these innovations, we classify thermal management materials into four categories. The first is thermal interface materials, TIMs. And these materials basically enhance the heat transfer between two surfaces. Second, the heat transfer fluids, HTFs. These are the liquids that facilitate heat transfer in cooling systems. And they play a very crucial role in industries like data center as well as applications like electric vehicles. Third, thermal insulators. These materials minimize the heat loss and they improve efficiency, and in some cases even act as a flame barriers. Fourth, we have the other materials, and in this category, we include emerging solutions such as radiator cooling materials as well as solid refrigerants. And these are some of the innovative approaches for thermal management. Now, let's dive into each category and explore the cool innovations that are happening across industries. In this section, we will first identify key unmet material needs in specific industries, then examine the current state of the art materials that are being used to address these key challenges. And finally, we will showcase a case study or a startup or a project which is actively developing solutions to meet these materials needs. So first, let's take a look at thermal interface materials. Now, if we look at a rapidly growing industry, which is electronics, where the thermal management is critical, here the heat transfer occurs from the chip die to the cold plate or the heat sink. And that's mostly happens through the TIMs. And the key requirements for the TIMs are you need high out of the plane thermal conductivity to basically move the heat away from chip. Then you need high in plane thermal conductivity to ensure the heat is evenly spread. And to maintain the efficiency under high thermal or mechanical stress, it's crucial to ensure good surface contact and low thermal resistance to avoid heat buildup. On top of this, you need excellent electric insulations to protect sensitive electronics component. So let's examine the status of thermal interface materials for especially electronics applications. And before diving into these details, let me first explain this heat map. So on x-axis, we have various materials commonly used in electronics industry. On y-axis, we compare these materials across different performance parameters. So the darker shades indicate better performance and favorable characteristics, whereas the lighter shade represent lower performance for a given parameter. And we have used this same approach across other categories as well. Now let's focus on TIMs. So we evaluated 5 types of TIMs material based on their performance parameters. So if you look at thermal conductivity, the newer nano-based TIMs and liquid metals offer highest out-of-plane thermal conductivity. Similarly, the nanotube-based TIMs provide a compliance with surface imperfections and handling the mechanical as well as the deformations effectively. So liquid metals soften as temperature rises, and that they also adapt to the surface irregularities. And it further improves the thermal resistance. However, when it comes to the ease of use, the liquid metal TIMs requires careful application. The circuitry first needs to be masked, and then only you can apply the liquid metals to basically prevent the short circuit. So we anticipate that innovations in this nanotubes and phase change materials will accelerate and will focus on striking a balance between the performance as well as ease of use. Now let's take the example of Carbice, a company that develops nanotubes, and it uses a vertically aligned carbon nanotubes in its TIMs. So Carbice initially focused on thermal management for satellites, but since a couple of years, it has also expanded into electronics application. So besides their high out of plane thermal conductivity, the key advantage of this vertically aligned nanotube is low thermal resistance. And this is because the nanotubes are compliant, they adapt to the surface deformation and ensure consistent thermal contact. So given its high performance, Dow has already partnered with Carbice, and they are integrating its silicon-based adhesives to target applications in electronics as well as automotive industries. And we expect this trend to continue, especially newer startups with focus on nanotubes will emerge. And one such example of early stage startup is Novolink, which recently raised funding to develop this nanotubes with carbon nanotubes, which will be targeting the TIMs for data center market. And this also highlights a growing trend in nano based thermal interface materials in general. Now, let's move on to the second category, heat transfer fluids. The next generation chips are already hitting a 1.4 kilowatt of TDP. So making this traditional air cooling insufficient for this data center applications. And that's driving a shift towards liquid cooling, especially in data centers. And we have seen three cooling types for data centers. So first is air cooling, and now it's ineffective because of the high performance chips. Second, we have direct to chip liquid cooling, in which the coolant removes the heat but doesn't really touch the chip. And third, you have immersion cooling, where the entire server is submerged in heat transfer fluid. And here, for effective cooling system, you need effective coolants. And for that, we have four key requirements. First, high thermal conductivity to remove the heat effectively. Then you need electric insulation, which is critical for immersion and leak-proof arrangement. You also need low viscosity to reduce the pumping energy. And finally, the important one is also low environmental impact, as many of the current coolants have either PFAS content or have very high global warming potential. So let's take a deep dive into different types of coolant used in data center liquid cooling. And as mentioned earlier, we are taking the same approach, types across the top and the most critical key parameters down the side. And if we look at the thermal conductivity, nanofluids are the winner due to the presence of ceramic nanoparticle, which basically enhance the heat transfer efficiency. But when it comes to the dielectric properties, a lower dielectric constant is preferable to prevent the electric interference. And among this, you'll see that two-phase liquids offer significantly better dielectric properties. Whereas for viscosity, the water glycol and two-phase liquids are well suited due to their low viscosities. Whereas the synthetic dielectric fluids have very wide range and making only few formulations suitable for this application. Whereas if you look at the environmental impact, despite their high performance, the two-phase liquids have a negative environmental impact. Whereas the latest synthetic dielectric fluids can be plant-based or biodegradable, and which makes them a suitable candidate or an alternative for data center cooling application. And here, a great example of the innovation in two-phase heat transfer fluids come from a recent collaboration between data center cooling and chemicals company. As you may know, 3M is discontinuing the production of its Novec and fluoroinert liquids due to the PFAS concern. And these fluids have been used widely in two-phase cooling application, and which creates a pressing need for alternatives. So to address this, Commerce partnered with data center cooling provider LiquidStack to develop a new generation of two-phase liquids. And the solution, Opteon, has a global warming potential of 148. And they are even further working on reducing it. And it has already gone through some testing. And the initial results show that the power usage effectiveness, PUE, with Opteon ranges from 1.07 to 1.15. And that depends on climate conditions and geography. So while this PU is significantly lower compared to the other liquid cooling solution and also the air cooling solution, there are several challenges here. The GWP and the handling requirements in large-scale data centers have basically slowed the adoption of this two-phase liquids. And as a result, in the near term, two-phase liquids are more likely to gain traction in closed-loop systems like direct-to-chip cooling, uh, and rather than applications in two-phase immersion cooling. So now let's move on to the third category, thermal insulators. So one key emerging application is electric vehicles and their battery packs, and particularly those using high energy density NMC lithium ion batteries, which have significant thermal management requirements. So, if we look at the battery pack structure, the TIMs are used to facilitate smooth heat transfer from cell to module to pack. While there are continued innovation, as we saw earlier in TIMs, the cell separators are also gaining interest as well. So, cell separators are basically insulating materials to prevent thermal runaway. And if a cell malfunctions, it basic or catches fire, these separators block the heat transfer and protect neighboring cells and eventually the whole battery pack. And from these advancements, three key requirements emerge. First, the material must have low thermal conductivity and should be able to withstand extremely high temperatures. Second, it should be lightweight and multifunctional, as weight reduction is crucial in EVs. Third, the materials must endure stress, especially in case of accidents. Uh, they should be able to keep their protective properties. So these requirements are basically driving the innovations in thermal insulators for EV batteries to ensure safety. And here we analyze three different types of insulating materials. So first, looking at thermal conductivity, all the materials in consideration have low values, but the aerogels stand out as they exhibit extremely low thermal conductivity. Next, considering the maximum temperature resistance, polymer-based insulators do not really perform well under this extreme heat, and which is also critical in case of thermal runaway. And in contrast, if you look at the ceramics and aerogels, they can withstand very high temperature. When it comes to density, you'll see that polymer foams are lightweight but lack the thermal stability, whereas ceramic materials vary in density. And while aerogels can be exceptionally lightweight, making them really ideal for the EV battery pack. So here, aerogel emerge as a best option for cell separators in EV batteries. And here, one of the companies, Aspen Aerogel, is developing aerogels specifically for EV applications. And one of the key products, Pyrothin, can basically withstand temperature up to 1400 degrees centigrade, and it has extremely low thermal conductivity. And because these aerogels are extremely lightweight, the EV battery pack can reduce the overall weight by 5 to 10 kgs. So major automakers like Toyota, Honda, GM have already integrated this Pyrothin into their EV batteries. And also to scale the production, Aspen Aerogel has already secured $670 million of loan from US Department of Energy in 2024, and basically now are expanding their second manufacturing facility in the US. While aerogels are highly effective in this case, but currently they are very expensive. And what we will see in the near future with increasing capacity in US as well as increasing competition from the APAC manufacturers, that cost will go down and we will see accelerated adoption of these materials. Let's look at the final category, that is novel materials, which go beyond traditional conduction and convection methods. And for example, passive radiative cooling, thermal metamaterials, or solid refrigerants. So one of the key markets here is the utilities company. There are concern about uh, basically their infrastructure and also looking for novel approaches to either reduce the losses in their systems and also focusing on improving the energy efficiency of cooling systems in consumer as well as industrial applications. And for the large infrastructure projects and other application, we need to look beyond the conventional conductive or convective heat transfer mechanism. And at the same time, the new mechanism, they should be cost effective and should have a low environmental impact. So here we examine three different materials. So passive radiative cooling materials and then two solid refrigerants. While they are not directly comparable, but understanding their characteristics helps us highlight their unique advantages and limitations. So, since these are new materials, let me briefly explain how they work. So, the passive radiative cooling uses specialized materials and structures to emit thermal radiations at a specific wavelength, so allowing the heat dissipation without or any external energy input. And this makes it fully passive cooling mechanism. Solid refrigerants come in two main types, the magnetocaloric and the elastocaloric materials. So the magnetocaloric materials, when they're exposed to magnetic field, they heat up and cool down when the field is removed. And this makes them useful in both cooling as well as in heating applications. On the other hand, the elastocaloric material works similarly but rely on mechanical stress. So heating up when load is applied and cooling down when once they are unloaded. So now looking at their environmental impact, all these materials have low carbon footprint. In terms of efficiency, the solid refrigerants can sometimes outperform the conventional vapor compression systems. However, they come when it comes to the passive radiative cooling, it operates on fundamentally different principles. So making a direct comparison with other systems is very difficult. However, there are some limitations, especially the temperature performance. And each system has a different temperature span. Basically, the effective heating and cooling range is limited. And these materials also face significant material as well as scalability challenges. So, for example, passive radiative cooling requires complex metamaterials which are very difficult to manufacture as well as optimize. The magnetocaloric systems rely on rare earth magnets, which are subject to supply chain shortages and geopolitical constraint. On the other hand, the elastocaloric materials use shape memory alloys like nickel titanium alloys, and their fatigue behavior is a major limitation. So most can only operate for a few hundred cycles. So while these materials show moderate performance compared to the conventional vapor compression system, they have unique properties such as zero energy consumption in radiative cooling, zero global warming potential for solid refrigerants, and which makes them worth monitoring in the near future. And as you saw, there are a lot of challenges, but despite all of these challenges, there are companies which are working on this. For example, Asset Cool has developed this specialized coating for overhead power lines. And these lines are made up of aluminum conductors and they absorb up to 50 to 80% of solar radiation, which basically causes the temperature to rise and directly impacts the efficiency of the grid as well as the current capacity of the power lines. And by applying this radiative cooling, the cooling coating, the heat is dissipated, effectively cooling the conductor and increasing the ampacity by 30%. Although this is still in the early stages. We are still waiting for the results from the pilot projects, including a 17-kilometer long test installation. However, the quick question remains regarding its commercial viability, particularly for retrofitting the existing power lines. And the company is already working on it, and they have also launched the robot for applying this coating. And additionally, there are some challenges in terms of how it performs under extreme weather conditions, which will be also critical for the widespread adoption of this technology. So far we have explored various material innovations and highlighted some of the most innovative startup addressing the challenges in thermal management. However, if we look at the last 10 to 15 years, we haven't really seen any unicorn emerge in this space. And there are several reasons for this. So one of the biggest challenge in thermal management materials is limited funding, as you can see from the graph. So scaling production for materials requires significant funding, but securing it is very tough in this sector. The cost is another barrier. So without economies of scale, many new materials remain too expensive for broad application. Then there are long qualification cycles, especially in conservative sectors like electronics and batteries. We see long qualification cycle. Incumbent competition adds even further pressure. You need to compete in a very crowded market. However, there are still innovation happening in thermal management materials and even accelerating. And with cost industry applications and massive potential, given the market size, this space remains a hotbed for breakthrough innovations. And it's a very vibrant market for both startups as well as industry giants. So far, we have explored the key challenges in this thermal management uh, materials, and then what our clients think or what the industry thinks about the challenges. I've also walked you through the latest advancement in novel materials and basically their progress towards deployment. Now, what does it mean for the future? Where should you place your bets? And how can you seize this opportunity? So the first key takeaway is focusing on new innovation applications. So the thermal management materials market is already saturated, especially in conventional application across industries. You'll see a lot of player already in the market. Uh, there's still some room for incremental innovation, but competing with this established player is extremely difficult. So the real opportunity lies in the emerging application where unmet needs still exist. So new companies should focus on these markets and develop the tailored products instead of trying to break into the established spaces. Secondly, the startups have struggled to scale in this industry. However, instead of viewing them as a competitor, incumbent and the material companies should see them as collaborators. If you already have a thermal management materials portfolio, partnering with these startups can help you strengthen your current portfolio. And if you are not yet active in this thermal management materials market, then startups or the small case uh, companies provide a strategic gateway into the emerging markets, whether through partnerships, acquisitions, or mergers. And finally, while we discussed emerging applications and their unmet material needs, technology is evolving across electrification, digitalization, and also climate tech value chains. So companies must monitor this ecosystem as a whole and look for these potential disruptors. And you must identify this potential shift and disruptors early on. For examples, in electrification, although in the early stages, safer battery chemistries are emerging. Similarly, what if you could develop electronics that no longer require TIMs? And likewise, also we have also explored the next generation uh, solid refrigerants which have zero global warming potential. And let me highlight a few interesting examples across different applications. So first, if you look at the zinc air batteries, these batteries are non-flammable and inherently safe and may not require the high performance insulators. However, despite their safety advantages, they still require thermal management materials to maintain optimum uh, performance over time. Next, let's look at TIMS free cooling solutions. For example, Fabricate Labs has developed a novel electrochemical additive manufacturing process to basically build copper cooling channels directly on to the chip dies. And this eliminates the need for traditional tips. But you still need coolants that can basically take the advantage of this cooling structures. Finally, emerging electrocaloric systems are being explored as environmentally friendly alternatives uh, as compared to the conventional cooling systems. However, there is still a huge scope for new materials development. So rather than seeing these as disruptor, think of them as opportunities. And by collaborating and innovating, we can develop the next generation of solutions for these emerging applications and make the most of these advancements. And with that, I conclude my presentation. Thank you.
All right. Thank you, Akshay, for that great presentation. We will now be taking questions that you may have on the presentation. Again, you can type any question you have into the question box that's on your screen. And if we do not get to your question on this call, someone from Lux will be in touch with you shortly. Obviously, I think you have already touched on it already, and it's the talk of all the industry circles that within our clients. And the first question we have is, which data center cooling technology will win?
I think uh, it's very hard to say, but what we see now is given especially in the liquid cooling market, almost 70 to 80% is direct to chip liquid cooling, and then immersion cooling is still, let's say, 10 to 20%. So given the system changes requirement, the infrastructure changes requirement, also the new material requirement, we'll see still focus on improving the direct chip technologies. And then subsequently, as the uh, TDP goes even higher and the current direct to chip systems cannot handle those TDPs, then we will see immersion cooling uh, also gaining some traction in next 4 to 5 years.
Okay, nice. And looking at the couple of the questions here, but one more here stands out, and I think it speaks to a lot of what you talked about in the presentation. Um, Clearly, there's a lot of thermal management materials startups out there, but they all seem to struggle to scale, as a lot of your examples were mostly larger players. So what have the successful ones done differently?
That's an excellent question, and I think there are a couple of things that come to my mind. And the first one is the business model. So, if you see the earlier thermal management material startups, they are very material focused. But now we are seeing most of these companies are product centric, and their business model is more product centric, and they do not depend on the sell of raw materials. And these products are now targeted at very high value applications. And basically, if you find that killer application, you'll be successful.
All right. Well, thank you so much, Akshay. To all the attendees, that concludes our webinar for today. As always, the slide presentation as well as the recording from today's webinar will be sent to all the attendees via email. Now, as you leave the webinar, you will be prompted to complete a survey on today's presentation. We greatly appreciate any feedback you may have to help us inform and improve our future webinars. And in the meantime, please take a moment and check out our upcoming webinars on the Lux Research website. Thank you all for joining us and have a great day.
Thank you.